Not yet. Maybe it's too low. Or
Yeah.
okay, so I'll bring it higher up. Here, do you hear me? No? Okay. I want to thank the organizer for inviting me. I'm going to talk about a general program that we are running with Fernando, who is here present also, and is going to talk, I think, on Thursday, of understanding constraint system, first order quasi-linear system with constraints. So we want to understand the whole theory, the mathematical theory of those systems. And we have made a lot of progress on that. But today I'm going to talk about not just the main program that Fernando is going to talk, but just on the boundary conditions side. So I'm going to talk about several related things on boundary conditions, give you the main ideas, the main theorems, and then I will tell you what the problems that we still are working on and what are the real difficulties there. So as I say, the outline is going to be that I'm going to talk about system with constraints, which is a program that we're running. I'm going to give you a short example of ADM, how we deal with ADM in this case. Something about the theory so far, but very little because it's going to be Fernando's talk, some more examples. And then I'm going to go to boundary value problem with constraints, when constraints are present. I'm going to revise the all results of CRIS, the new understanding that we have of the problem, and recent problems that we have, the open problems in this. But I'm going to do it in the setting of the new approach that we are having. So let's start with the basic things, the basic notation. We are going to deal with system of equations here. The big A denotes the number of equations. The alpha is the number of fields, so this is a multi-tensorial index, maybe scalars, vector, tensor, metrics, etc. So GR is going to be here, written in some way. Some source terms that depends on U, and the K, this one depends also on U. And this is a space-time index, so this is the only index that enters in there. So we are going to call the dimension of the E, the dimension of the equations, and the dimensions of the fields. And in general, we are going to have that there are more equations than fields. So it's not a square system in general. So we have many more equations than fields that we want to solve for, and that's why we have constraints. So that's the whole setting. And we call the constraints, and we are going to see that there is a good definition of constraints. It's just the difference between the number of constraints of the equations minus the number of fields. And when this happens, when these are constrained in a way we are going to define later on, we say that the system is consistent. So the message is that there is a good definition of what we mean by constraints in this. As I said, the theory we know for hyperbolic system is a system where this metric is square. So we have the same number of equations as variables, right? And this is well-known theory from the 50s. And there are many ways of characterizing the system, which is basically in an algebraic way. And this is the work of basically the celebrated matrix theorem of Kreis that I'm going to show you later on. So that is the theory that we know. So in many places I'm going to do a 3+1 decomposition or n+1 decomposition. So we take some some vector field here transferred to surfaces, and locally we split things into the surfaces and also on the direction normal to it. And so from the big system we define this other system. We have the t derivative here along this vector field, and we have this matrix A that is this combination. And so the first thing we require is that this K be invariable, right? This is for the square system. And so many things we are going to refer to this metric, and sometimes we are going to put this on the other side and we refer to the covariant way of dealing with this, with the case. So that's why the notation is because I have things in one notation or in the other. So let me give you an example of what we are doing. For instance, if you take the Einstein's equation in the ADM form, you will have an equation for the metric and then an equation for the extrinsic curvature. And then you have two constraints equations here. And we take this function here, the lapse, that, well, doesn't appear already here. What the relativists call the lapse, that is a function that appears inside here. We say that is some square root of the determinant of the metric times some power b times q, and q is fixed. That's the gauge condition, and the shift is 0. So those are the equations, and we go to the this is the constraints, the scalar constraint and the momentum constraint of the theory. So these are all the equations. And now what we do is we go to Fourier transform, look at some point and do local Fourier transform, and get this pencil, this matrix pencil. So lambda varies here, and this k here is the wave number, the three-dimensional vector field. And so we, from the other system, we get this matrix. And now here we have introduced a new variable to make it the system first order. We call L. Here is that h times the norm of k, of the wave vector. So this way we make a pseudo-differential operator, which is first order. And that's what we analyze. And to analyze it, what we do is a Kronecker decomposition of this pencil, this metric pencil. And when you do this Kronecker decomposition, you get this system here, this metric here. And here is all the information we need to know about the system for proving whether it's well posed or not. The physical degrees of freedom of GR are these two. One here, lambda is plus minus 1, so the kernel of that is lambda plus minus 1, so one is the speed of light. This square here is a gauge condition. That doesn't matter, doesn't do anything. And here we have a split with the beta, and we are taking beta equal to 0. If we were going to take beta equal to 0, then there will be a 1 here. And so we will have a Jordan block that is of dimension 2. And in that case, we know that the system is ill-posed. But for b different from 0 is well-posed. And these here, which we call L1's blocks, are the constraints. We have 4 constraints, one for the scalar constraint and 3 vector constraints, and we get these 4 L1 matrices here. And from that information, just seeing this metric, we can conclude several things. As I say, that if b is equal to 0, the system is not well posed. There is a 2x2 Jordan block. And in fact, for doing that, we don't need to do even the Kronecker decomposition. For beta different from b different from 0, it is well posed. And for that, a bit more work is needed, but you can show that it's well posed. And also, you know that the constraints are well posed. They propagate with speed equal to the subset of the propagation speed of the main system. So we know that this system is okay. We can put now boundary conditions to it so that we ensure that the constraints are satisfied, etc. And that part is what I'm going to tell you today. I will attempt to do all the arguments to show this.
Excuse me, could you say why does, if the Jordan block is used, why does it mean that it's still posed?
It's still posed because to have the system well posed, you need metrics to be diagonalizable, and that prevents that. So any reduction of the system you want to do, you will find a block that is non-diagonalizable. Okay, and that's prevent. Yes, it gets smaller. Okay. Yeah.
So you want the eigenspaces
right.
suspendable space.
And if you know that you are missing one eigenvector, then you know that you can build a sequence that is going to blow up at any finite time when you go in frequency to high frequency. So that's the easy to show that if you have a Jordan block of dimension larger than 1, the system is ill-posed. it's much difficult to show that if you don't have any Jordan block, the system is well posed. You need more characterization of the thing. So that's what Fernando is going to talk about.
So if E is equal to 1 and Q is a constant, is that the same as harmonic selection?
I guess so. I haven't done the calculation, but I'm pretty sure of that. But here is a point which is important. The reduction that we do is to show that I'm going to tell you what a reduction is and why it's pseudo-differential and so on. The reduction we need to do is only pseudo-differential. So we don't get at the end of the day equations which are differential. We have pseudo-differential equations. So for instance, if you want to put in the computer, you might be okay using a pseudo-spectral code, but you cannot use, say, finite difference for this. But nevertheless, you know that if you give data, the solution is going to be continuously differentiable with respect to the initial data in the usual Sobolev norms.
So what precisely do you mean when you say constraints are well posed?
That the system of the subsidiary system, that is the system that the constraints satisfy, they are also strongly hyperbolic.
And it's required that their characteristics be the same, or that's a separate observation?
They are going to be the same. That's a theorem.
That's a theorem.
Okay. It's, I'm going to argue at say mostly the end of the talk about this. There is a theorem, and why this theorem has to be true. I mean, the motivation for this theorem to be true. But that theorem has some conditions which are not always satisfied. So there we have a problem. Here in this case, it's okay. Yeah.
About your last comment, so we used to say that if you have a system of equations, the particular discretization method will take, well, might be harder or more difficult to implement, but if things are okay, then there's no preference on the method itself. It might be a practical preference, but any discretization method should be able to get a solution. But here you're saying in this particular case, that there might be some methods for which you could get a solution, but others that would not at all.
Yeah, because the reduction, it means to have a reduction means you will take some of the equations, some linear combination, and use those as evolution equations. But those evolution equations are not differential equations in general. They're only pseudo-differential. So you might argue that, okay, you can compute, do approximation, everything is okay because it's a stable system. But you will not be able to just go get those equations and put on a finite difference algorithm because you don't know how to do it. It's not local. That's a very bad thing. But that there are some operators there that to apply them, you go to Fourier transform, apply them there, and come back. So, for instance, if you do a spectral code, you could do that. I mean, you could go get the U-hats, do your operation, and come back. But it's non-local. Yeah, but it's non-local. I mean, it's going to be some big stencil of the size of your system or something like that. But in the end, we have to go to this bigger space of pseudo-differential things to work, because in the differential setting, symmetric hyperbolic setting, you don't get everything. And we know that there are counterexamples. So this is mostly the right setting, I would say. So let me go now with these first-order systems. I'm going to follow Geroch's paper, which I recommend for people that are beginning in this topic, because it's a very nice paper with have everything you need to know at the beginning. And so he gets these systems, and then he defines what a symmetric hyperbolic system is, or he will say admits a hyperbolization. If there exists this tensor here that has an index in this equation space and an index in the fields, such that this combination, which has two indices down, a field index here, is symmetric and there exists some vector field NA such that this combination is positive definite. Right? If you find this H, then you know your system is symmetric hyperbolic. Most of theories in physics are symmetric hyperbolic, so this is enough, basically, for MHD, Maxwell, GR, etc. You find always symmetrizers.
Is that index on N supposed to be a B, or is it supposed to be
A B, yeah.
Okay.
Yeah, this is a B, sorry.
And also on the first, in the first equation, A and B are the same. In Garrett's.
Yeah, I guess I'm bringing from here the mistake and replacing things, yes. Yeah, that's contraction here from this. So we are going to, instead of talking about hyperbolizations, we are going to talk about reductions, which is basically the same, but essentially, but we are going to have some linear combination of equations, which will give you the same amount of fields and equations. So this H now has the index up, and we don't require in the beginning that this be hyperbolic. So we require that it goes from the map of equations to the map of fields. And in general, this is to illustrate that this is what we call usually an evolution equation. Just from there we get evolution equations. And that is by no means unique, because basically you could put the constraint once I define the constraints, add constraints here to these equations, and get a lot of equations. So evolution equations in general are not well defined. When people say this is evolution equations in general for a constraint system, they are making assumptions. Unless the system, of course, a fluid, for instance, doesn't have any constraints. So when the people say this is evolution equation, it's a whole set of equations, and that's okay. When you have constraints, the evolution equation doesn't have a meaning. Right? You have to say more about that. The constraint, no, the constraint have a very unique meaning.
Why do you say fluid, but if you don't have constraint, and the divergence constraint and all the equations constraint?
Okay, if you do uncompressible fluids, yeah, then you have a I'm just talking about fluid in general, the compressible case. Yeah, in the incompressible case, it's the same. You have the same problem. So another definition that comes handy because it's better than and is weaker than symmetric hyperbolic is strongly hyperbolic. In that, once you have a system like that, you say, okay, this system is going to be strongly hyperbolic when I find a symmetrizer now that also depends on K, such that this combination now in gamma and beta is symmetric. So you require this to be positive definite and this to be symmetric. And this is the widest class of system which admit a well-posed formulation, the strongly hyperbolic class. And so we're going to work on this class. Notice that for this, I have already put my system with a reduction. So we are going to talk about strongly hyperbolic system when we apply a reduction. Right? And we are going to say the system is well posed if there exists a reduction such that the system is strongly hyperbolic. If you have either symmetric or hyperbolic or strongly hyperbolic system, what you get they are energy estimates. Energy estimates allows you to estimate the norm of the solution at some later time from the norm of the solution at the initial time. Right? In the case of symmetric hyperbolic system, you get the usual energy, namely Sobolev norms. In the case of strongly hyperbolic pseudo-differential, you need pseudo-differential calculus. This is a very messy thing, but you get at the end some Sobolev estimate also, but that requires a lot of work. So the operators here in the strongly hyperbolic case, they are pseudo-differential operators, and you have to use pseudo-differential calculus. That's not nice, but fortunately for physics, most of the systems, as I say, they are here. So the question is, when does there exist a reduction such that the resultant system of evolution equations is well posed? Until now, what we have in GR was that, okay, we get some equations, we start mumbling with the constraint, mixing constraints, etc., and trying to check whether we get the system to be symmetric hyperbolic or strongly hyperbolic, computing all the eigenvectors, etc., and see that you get a whole system, etc. And was a sort of try and error. And you could, if you discover that the system was well posed, okay, you were okay, happy. But if you couldn't find a hyperbolization, some evolutionary equations were hyperbolic, you didn't know whether the system was hyperbolic or not, because you don't know whether you exhausted the whole set of hyperbolizations possible, of reductions. So what we want to do is to systematize this problem. And this is, you have to wait for Fernando's talk, because I'm not going to go into that part today. So, but let me give you the Kreis matrix theorem, which is going to help us a bit in this. So he says, okay, if you want to have a system that is well posed, this is equivalent to say this matrix A that appears there, the one that I defined there with the case to the -1, has to be, this combination has to be bounded as matrices by some constant times t. This A, remember, has the k, so this is for all k that has to be bounded. This is equivalent to this symmetric hyperbolic condition or strongly hyperbolic condition that exists at an h, such this is symmetric, positive definite. And this is the condition I'm going to use now that says, okay, the A has to be diagonalizable. Of course, there are some uniformity conditions on this, so the S has to satisfy some conditions, it has to be bounded by above and below, etc. And then there is this other resolvent condition that Fernando is going to use, so I'm not going to say anything. But this, the third one, as I say, is the condition that this metric A has a complete set of eigenvectors. And that's nice because it allows us to do a geometric, to have a geometric view of what is going on here. Imagine you go into tangent space, so you have these vectors k here, and you look at these lines, and you contract this k with the lines. This, the S goes from minus to plus infinity, and you take this k be different from, not parallel to n, and you get these lines. Since this doesn't care about the norm of n, this is just the direction, the manifold of directions only that is interesting. So we get some, in the projective space, we get these curves which are connected from here. So they are closed curves, non-simply connected curves. And these are the characteristics of the system, namely the case for which the points here for which this has a kernel. So these are these lines. And the condition that system is symmetric hyperbolic or strongly hyperbolic is that when you transverse all these lines here, the characteristics lines, at each point of here, the kernel is maximal. So you get the kernel as big as possible. Right? So the algebraic multiplicity of the polynomial that you are having there is equal to the multiplicity. So, and this is nice because, for instance, now you say, okay, if I take a different n, like this, for instance, a curve that comes from this point, goes like that, and comes to the other side. This is on the back of the sphere. Then this is going to cross here and here. But here, at this point, we can see the kernel either from here or from here. And we know that this kernel here, because it was strongly hyperbolic for this line, that here the kernel is maximal. So in this line, this kernel is also maximal. So that allows me to move the point and get a convex hull to show that the ends form a cone, which for the strongly hyperbolic case is not so easy to see. For this symmetric hyperbolic case is very easy, but for the strongly hyperbolic case it's quite complicated. But if you have this geometrical picture in mind, then it's easy to get the results. So let me go now to the constraints. So now we know what a symmetric hyperbolic system is, and we want to see what happens with the constraints, which is the other part of the equations. So you get you start with the system like this, and you find fields with this set of indices such that when you contract them like this and symmetrize, you get 0. This C has this property means that when you do this combination here with M being the normal to a hypersurface, this set of equations have only derivative along the hypersurface. So they are really constrained in the sense that we think of constraints, since that you have to prescribe as equations in some hypersurface that they are not contained in the time, right? So this is that definition captures the right condition. And as I said at the beginning, if the system is consistent, if the number of constraints is equal plus the number of fields is equal to the numbers of equations. So we don't have any extra equation that we don't know what it is. Can be, there could be some, there are some equations that are inconsistent, so we get an inconsistent system. So constraints are well defined. They define a subset in this manifold, right? They are contrary to evolution equations. They are very well defined.
So I mean, normally we sort of think of these as constraints when n is finite, but from what you've written down, it seems like this works just fine if n is space-like or no as well.
Right. So the general theory doesn't have any metric or anything time-like. I keep saying time-like because I'm the relativist, but right. Here there is no need.
Yeah, okay.
The ends are characterized in this way, that you will get some cone, but this cone doesn't have anything to do with the metric cone. Yes?
So just elaborate a little more what you said, constraints are well defined. If I take different slices, but I'm not change what I'm constraining, the derivative if I take a mouse slice.
Yeah.
Right, so then constraints are significant. So which sense are you?
I mean, these C are well defined. These things here.
But I mean, the students make combinations of them and create a family of equivalent constraints. So that's what
Yeah, I mean, they form a subspace. They are not numbers, right, or functions. They form a subspace. That subspace is invariant in that sense. And of course, when you want to get quantities, then you set some coordinates there and fix some n and do it. But that's a posteriori. That's when we fix the n for this, doing these pencils, for instance. That's why we get there. But at this level, they are very general. So let me give an example. If you take electromagnetism in the covariant way, you have 6 variables. The F is antisymmetric. And you have 8 equations, because you have 4 here and totally antisymmetric tensors in 4 dimensions have like a vector. So you have a total of 8 equations. So we have 2 constraints. We know what they are, divergence of E and divergence of B. But here, if you write down the equations in a Lagrange with this K, you will get this is the K. The beta index is these antisymmetric indices. And the equations indexes is A here, or well, the B here in the totally antisymmetric sector here. And you can find the constraints and the C's. These are the K's, and the C's are these. So a linear combination of a 2-dimensional space of C. And what they give you is divergence of E and divergence of B, where E and B are defined in the usual covariant way. So now I'm going to need to introduce a bit of the Kronecker decomposition, which is something that we don't learn in algebra, but at least not in Córdoba, but we should learn, I think, because it's very important, very neat. So it refers to the composition of pencil matrices, namely one parameter family of matrices. So we define these pencils, and then the Kronecker decomposition says that there exist 2 matrices here that depends on K, because everything depends on K, such that this metric can be written in this way, where these two matrices here have the following form. So there are identities here. Well, actually, these are Jordan blocks, no identities. And then there are some other matrices like LM3, LM4, etc., which are matrices that has this structure. So they are a bit longer than wider by 1, and have this S in the middle and then a 1 below. So it's like a Jordan block, but with a 1 extra row here. And here we are assuming that this K times N was invertible, or not invertible, was maximal rank. Right? And this is necessary, otherwise the Kronecker decomposition have two more type of matrices. But for this system, so that for evolution systems, for systems that you want to solve for hyperbolic system, this is the most general case. And in practice, the Geroch constraints are these L1s or L0 blocks. L1s are the ones that have, remember, a 1 and a 0, and the 0 blocks are blocks that have just 1 0 here. Those are the only ones that appear in physical systems. You can get some other system examples where you get other blocks, and you can do evolution of those systems, but they don't represent physical systems. I think that's why we haven't discovered them before, but they are there. So let me give you the decomposition of Maxwell's equation in E and B. So if you write then these linear combinations, you take K to be in the z direction and N to the time direction. So you put coordinates like that. Then you get these that are the physical fields, so Jordan blocks of dimension 1, and then you have these two constraints, the L1 constraints. And the reductions, what they do is, for instance, is a matrix like that, so that once you multiply, you get a matrix which is square. And this constant here give you the propagation speeds of the constraints. So this A and B acts on these two parts. And what it does is take these two L1s, which are two rows, two columns, and make a one-dimensional column of each one, and it's a new row for the system. And you threw the other away. And this way you are mixing the constraints and get the propagation. So these are the propagation speeds, and you can choose them arbitrarily because we are just propagating constraints. And this is going to be reflected in when we study the system that the constraints satisfy, the same velocities are going to appear, the same eigenvalues. So now we go to the boundary value problem. So we imagine that we have a Cauchy surface here, and we want to evolve in this region, and we have a boundary here, and we extend this boundary along some vector field for a while. This is a local construction. So in the case of Einstein, we are going to look for solutions in this region. So this is the cartoon of the situation. We have a boundary, a space-like boundary, and a time-like boundary for Einstein, or Maxwell, or wave equations. From the initial surface, we can determine a unique solution here, but from getting the solution there, we need to prescribe what are the radiation fields going in. So we have to do some prescription for that, and once you have this prescription, we can fill this thing, this glass, and get the solution in the whole region. But we need to prescribe things here. Right? These are the boundary conditions. And these fields that enter here, we distinguish three types of fields. The real radiation, whatever that means, I mean the equation that you will say, this is physics, this is the thing that the LIGO measures, or if it is electromagnetism, when I put my pot, it's going to be make it boil. Then there are gauge modes, which are prescriptions you did something to fix the gauge, This is basically constraints also. So we have this gauge mode. And then we have the constraint mode. The constraints are going to propagate somehow. This, by that I mean when we do the reduction, we have this A and B there sitting, and this is the propagation, will give me propagation of constraints. So these are well defined, and in fact the gauge mode also, because once you fix the gauge, these gauge modes become constraints, and once they are constrained, we know how to deal with constraints in the whole generality. So we have this case. And of course, the treatment of these things is different, because radiation is a physical quantity. You can say, for instance, I don't want any radiation coming in. That will be a physical condition. But these two are not physical conditions. We have to prescribe them in some way so that the gauge condition or the constraints conditions are satisfied. Right? So they are not free. So we have to do something. So let me flash this because we need some concept here, which is important. So if we have this equation, for instance, then we know that the modes move to the left. So when we reach this boundary, we don't have to give anything. The modes are just going out. We just don't prescribe anything. And if we look at the energy that defined that way and take the time derivative of the energy, you do the usual integration by parts, you get this thing. So this is the value of u here in the boundary at x equal to 0. And from there you get this estimate. You integrate this condition here, and you get that the energy at time t plus the integral, so the energy here, plus the integral of E squared here is bounded by the initial data. The integral, this f is the initial data. So we have control not only of the value of this solution here, but also on the boundary, on that boundary. If the mode is incoming, you have to prescribe it. So on top of prescribing the initial value, you have to prescribe the value of this thing, which should appear here, but it's not. So, but you do the same calculation, you get this thing squared. So if you prescribe, there it is. If you prescribe its value, this thing is known. So I can just add and subtract this. So we get this, and we can add and subtract u squared and get the following estimate also. So we have E times the value of u squared in the boundary, that you know how much it is bound by the data here plus the data in the boundary. Right, so you know all the things. So you know that you have a norm here in this region. But what happens if you have this equation here? So the wave is just standing there, doesn't move. Then you get an energy estimate. The energy at the end is equal to the energy at the beginning, but you don't get any control on the boundary. Right? And this is okay. You say, well, who cares? This has a solution, etc. But if I want to play this with a quasi-linear system, say Einstein's equation, then I will have to make estimate in the boundary, estimate my solutions, etc. And if I don't have a control on some terms, then I'm lost. I cannot do it. So this is a main problem. This case is the characteristic case. So in the literature, people just say, my system is not characteristic, meaning that there is no way coming like that. And then you get a theory. But if you have characteristics, then you are lost. I mean, in the generality of the system. So we don't get control on the boundary. So the old theory of Kreis from the 70s assumed that you have this metric characteristic. So you put initial boundary conditions, and you show at the end that it's strongly well posed, which is this condition, namely that you, from the initial data and the boundary data, you get a solution, an estimate on the whole boundary here. This is the top, and these are the sides. And this is a concept of strong well posed system. If the system is strong well posed, you can do boundary conditions, many ones, I mean quasi-linear, etc., because you control everything. But in general, for having that, you need that this metric be non-characteristic. So there is no wave going on the surface, on the boundary. Yeah, but remember that this is a cartoon case. In general, you will have an equation, some evolution equation, where sources are or derivative of the other fields there. So that's a problem. When you try to do the nonlinear case, you don't have enough information. And people have tried a lot of things, that there is a lot of literature on that. Even Kreis has some cases in which he can deal, and then there are some other. I mean, there is a whole industry of papers on that. But let me illustrate the problem with, suppose you take now electromagnetism in the gauge potential case, four-dimensional gauge potential. You put a divergence gauge condition, which is the divergence Landau conditions or Lorentz condition, and you get a boundary at x equal to 0. Then from this equation, taking the divergence, you know that you get that the divergence of A satisfies also the wave equation. And this is what we refer to the subsidiary system. This is the system that satisfies the thing that should be 0. Right? And if we are going to claim that this thing remains 0, we have to put boundary conditions such a way that this equation here doesn't have any incoming mode of this that will violate the constraints. So, for instance, if we put divergence A equal to 0 in the boundary, we are going to make sure that because uniqueness of this system, that this is going to be preserved inside, so we are going to have this condition valid everywhere. And if, of course, if we put in the boundary, in the initial conditions also. So if you say, okay, I'll get this system, I will, I get this condition here, my incoming mode. This is the outgoing mode. I can prescribe things for this. And here I have this is a 0 mode, namely this thing goes along the boundary, this also. And this is a condition here, for instance. If I want to go put the divergence to be 0, this is a condition I need. Right? This is the divergence. So, and this mixes these two modes with these two modes here, the modes that come here, from here. So I don't have any way of asserting that I can bound these things and get an equation for this. This is not good. I cannot decide what this value is in the boundary. It's going to be given by the evolution. So I cannot do it. And this was actually a problem until recently. We didn't know how to do boundary conditions for Maxwell's equations in Lorentz gauge. Right. So I'm going to show you how to do it. So that's, and in GR is basically the same with more fields than Maxwell's in this sense, in the structure of the things. So in general relativity, we have this problem of characteristics, and this was solved first by Helmut Friedrich and Gabriel Nagy, 1988, and then by Kreis and Winnicott, and then we have a paper on the same. And basically all these things, all these methods were finding a reduction where you didn't have any 0 mode. That was, in the end, once we learned the things the right way, it was was what we were doing all the time, finding reductions which were okay. But at the moment, we were very much on darkness on this. It's a complicated problem, and there is still a lot of questions which are open, in particular the geometric uniqueness. We don't know whether the solutions we get in one gauge are the same as solutions we get with some other prescription, and this is fairly open problem. So it's there, it's sitting. There are very few people working on that, so it's very nice problems if somebody wants to tackle it. It's difficult. So let me tell you in a slide what the results are. So you get now you are going to use second order equations like this. This is, for instance, GR in the harmonic gauge that Franz was talking about using. So you put initial conditions for the fields and the derivatives, and boundary conditions. And the boundary conditions you put in this way. So time derivatives times the normal to the boundary with this constant positive times, if you are at some field, you can put derivative of the fields that were done before, and then small pieces of all the derivative you want, times some sources. So this is a upper triangular way of giving derivatives. In the end, I'm going to show you an example. So if you have the boundary conditions like that, you do a trick to make everything small, and then you have a theorem that says the problem is strongly well posed. So these boundary conditions are strongly well posed. And once you know that, I'm not going to go through this theorem, but once you know, I'm going to use it for solving this Maxwell equation problem. So we have this problem with the condition. And now we do the following. We take this boundary condition. This is just a gauge field, basically. These are the Sommerfeld conditions. So these are radiation, real radiation. And this condition here is equivalent to divergence A equal to 0. But notice the following. This condition has part of this derivative, which are already solved for, part of this, which are already solved for, and derivative of this field, which is already solved for. So this system like this, and all have the A here is with the right sign. So it was on the other side positive, so here is negative. So this system is strongly well posed. So I can do this. I can handle these terms, which prior were not able to, nobody was able to handle, because these boundary conditions are okay. And for GR, the thing is basically the same. So basically, one thing is important. Here I show you, with these conditions, I can ensure that the divergence of A is equal to 0 at the boundary. Then I use the subsidiary condition, which was this equation that was block divergence equal to 0, to show that this is 0 everywhere. There are many more boundary conditions you can use. This is not the only. And in general relativity, in the harmonic gauge, the problem is very similar. You can solve it the same way. So let me now go to the, I have only 10 minutes, to the problem that I want to discuss more in detail now, these L1 things. I mentioned that we have a radiation degrees of freedom and some constraints degrees of freedom. We'll just put them in red here in some direction. And we have the, ideally we will have to say, we want to say in physics, okay, the number of fields is the radiation field, the physical field plus constraints, and the number of equations is equal to the number of fields plus constraints, so you get this equation here. So the equations are radiation plus twice the constraints, which is for since a system that comes from Lagrangian variational principle, this is okay, because for every gauge condition that you will turn into constraint, you get another constraint, so you get twice a constraint. But this is sort of, this is true under some conditions. This is Wonderland, not the real generic case. I'm going to talk now about the generic case, where this is no longer the case, and I want to explain. But for the moment, let's say this is the case. So imagine in the case before, we have this situation. We have the radiation field, the constraint fields, and the subsidiary system. Let's say instead of being all along this direction, they are some other direction, which is different from this one. Yes. So we imagine that we have a propagation for the constraints mode in this system to be the red ones, and the propagation of the subsidiary system to be these different ones. Then you say, okay, in this case, I can get all this information that I get for free, because this I can prescribe. to cancel all the degrees of freedom that goes inside here. So I can make the green thing 0, choosing the right things for the red. But they say, well, this is not good because the following. If I move and take another surface, which goes like that in between these two characteristics, then I'm lost because now I don't have anything to prescribe to kill this, right? Because the things that were helping me and now are going out, I cannot give anything about this. So I'm lost. I cannot control the constraints. So this picture is wrong. Or we are in a problem. And in fact, it's wrong. Modulo some conditions, and what you get is that the propagation speed of the constraints are the same as the subsidiary system. And that has to do with this decomposition on the L's. And when you look at the subsidiary system, you get the same structure. How do you see this? I'm going to, maybe I'll skip this. Well, let me just tell you quickly. These are the equations we had at the beginning. These are the constraints as defined by Geroch. And so you require now that you will get a subsidiary system like this. From Geroch work and some more work, you can see that there is always a system like that, provided something happens, which is okay. I mean, it's in the setting, the original setting. So you can guess that this S exists. We don't know whether it is unique, but we know that an equation like that exists, at least one. So we have now an evolution equation for the constraints. This is a subsidiary system. And now so we get the constraints, you get this subsidiary system. Sorry, this is a subsidiary system. This twiddle means here up to principal part of the equation. We don't care about the other parts. So we take a time derivative of this, and we get this using the equation for the u. We get this equation, and if you take the b's and use this definition, you get this equation. So you see, this has to be equal to that. In Fourier space, you are saying that you have this condition here. And now imagine that you have an eigenvector of this A times K. So this is an eigenvector here. If you plug this eigenvector here, on this side you will get U again times C, which will make B. And on this side you will get, when you put the U, you will get a B. So you will get this other condition, right, when you plug these things here. So that means that for every eigenvector U of the original system, I get an eigenvector of this system with the same eigenvalue. So now, if you know that this expands the whole space because this system was the initial system which was strongly hyperbolic, and if now you require that this combination has maximal rank, then you find that all this combination of the B's also span the whole space of the constraints, and so you know that the space of the constraint have a complete set of eigenvectors, so the system is also strongly hyperbolic, and with the same characteristics, with a subset of the characteristics. So this way you prove that the subsidiary system is also strongly hyperbolic. It's not true that if you get a system which is symmetric hyperbolic and the subsidiary system is going to be symmetric hyperbolic. That's not the case. So there are symmetric hyperbolic systems where the subsidiary system is only strongly hyperbolic. That's why you cannot stay in the class of symmetric and prove these things like this. So that's why we have to. Well, I'm going to I don't have enough time, so I'm going to skip this. I'm going to go. Okay, I'll tell you what the problem is. I said, okay, you have this maximal rank condition, but now take the wave equation here, written as a first order system. So you have the phi, and these are the derivative of the phi. And you get this. This is the system, basically a wave system, and this is the integrability condition. And so this system has a symmetric hyperbolic formulation, and these are constraints. But notice the following. You have 5 degrees of freedom, phi, 1 for phi, and 4 for here, which are 2, which are the real degrees of freedom of the wave equation, plus 3 fields. But you have 11 equations. So you have 6 constraints. So you have more constraints than fields. So your maximal rank thing fails miserably. You cannot control all the constraints with your fields that you have only 3 fields to evolve. So here there is a problem. And how you see this problem in the Kronecker decomposition? Well, the Kronecker decomposition of the wave equation is like this. You have these L1 modes here, 3, and then you have 3 constraints which have 0 here, L0s. What does it mean? The sum of the constraints are linear combination of the others. That's why you get 0 there when you do the Kronecker decomposition. So you shouldn't care about them, but they are and spoil everything. And you might say, okay, what is going on here is that notice the following. If this constraint is 0, then if I plug this L to be the gradient here, this is also automatically 0. And you say, okay, this is a condition, right? But wait, in the Kronecker decomposition, I'm not looking at the L because we are looking only at the principal symbol. So it's another condition, which is related, of course. And that condition is, just to close, is when you go to Fourier space, the C is proportional to this in the plus the L, which it doesn't care because it's lower order. And so, and the Cij is like this. And so this combination is the one that is creating the zeros in the Fourier space. So this is the real problem. And we are handling now, we understand what it is, and we are trying to extend the theory of those for those cases. Okay. Thank you.
Okay, we have time for 1 or 2 questions. All right, let me ask the question then. So, suppose I have a harmonic code, and now I want to introduce an outer boundary condition that preserves the constraints and that somehow means no incoming radiation. So, is there in your prescription a sort of a way of doing that? And if so, what does it look like?
Well, it looks like there are some Sommerfeld conditions, right, for the degrees of freedom that you think are there radiation. Yeah. And then there is a bunch of conditions that will guarantee that the gauge and the constraints don't come in.
Okay.
So
but
this.
But I can like read these things off. From,
yeah.
Your place in your paper, for example.
Yeah.
Okay.
I don't think I have it here, but I mean, at the linearized level, you can see it's the same, basically, with one extra index.
Okay.
And it's nice. The structure is nice.
The theorem that you showed about well-posedness of the initial boundary value problem relies on having sort of wave equations that are decoupled in the principal part.
Yeah.
In the evolution equations, and then the coupling just comes with the boundary. I'm wondering, did you think about whether or not that proves to be generalized to have a more complicated or more subtle structure in the principal part?
You mean something where the principal part depends on the derivative also? Because here you allow.
For example, where you've got second derivatives of one field standing in the box operator of another field.
No, because there you go out of quasi-linear.
No, it would still be quasi-linear. So you could have something like, box phi, and then you've got, I don't know, grad phi or something. Or
grad
pi. So a different field, but second derivative of a different field standing.
Okay.
Like that does happen in GR. That does happen in some gauges.
Yeah, no, that we don't include. The proof is very particular to the wave equation, in some sense, but maybe we can talk about it.
Yeah, this sounds like a good discussion for the coffee break.
Yeah.
So let's